So the second talk of this opening session will be by Klaus Kiefer. So Klaus Kiefer has been professor for theoretical physics at the University of Cologne for at least 20 years. So his research interests are mainly based in quantum geometrodynamics, so very conservative approaches to quantum gravity. But he is also very famous for all the reviews that he has written and also many, many public articles that appeared in German popular science journals like Spektrum der Wissenschaft. And then what I really hold in very high regard is his textbook on quantum gravity. So this is really an invaluable source and one of the rare books that really tries to go beyond a single approach of quantum gravity and give a more a broader review on the field. So it's a pleasure to have you here giving the talk, and the floor is yours.
Yeah, thank you very much for this kind invitation, this kind introduction. It's of course a pleasure for me to be here. So in the following half hour, I try to give a focus on one issue in quantum gravity, the problem of time. Now because, huh?
You're out of view with the camera.
Because of the camera. Oh, sorry, I did not know. Still very old-fashioned, I must say, walking around in the lecture hall. The issue of time. Now, this is, of course, a comprehensive topic. So in this half hour, I decided to give a conceptual introduction, also, of course, with a personal focus. So many topics are left out in this short time, but I hope it will be a coherent presentation. Now, there are four sections, so I divide up the problem of time into a classical and a quantum version. So this is problem of time 1 and 2. Then I say something about a recovery of semi-classical time, semi-classical gravity, and the coherence, the word that has just been alluded to in the last question, because this is related indirectly to the problem of time. And finally, I say something about the arrow of time, which is the origin of irreversibility in our universe. Can we understand it from quantum gravity? Now, it's always good to start with a quote by Einstein, and I selected the following one. He wrote a foreword to Max Jammer's book on the concept of space. So it's about space, but it also refers on time. And in the English translation, here's the original in German. It took a lot of struggle to arrive at the concept of independent and absolute space and time. This is, of course, what Newton did, which is indispensable for the theoretical development. Otherwise, I mean, we could not have constructed the gravitational law. And it has taken no less struggle to overcome this concept afterwards. There, Einstein refers to himself, of course, to 1905. And then he writes a process that is probably by no means finished. And this, at least, we can allude to quantum gravity and the discussion of time in quantum gravity. So you all know that general relativity is still our best, experimentally best, theory of gravity, and the Einstein field equations that he presented first on that date, of course the cosmology constant 2 years later, give this very intricate connection between matter, energy, and space-time curvature. So on the left we have the geometry, the gravitational field, on the right the matter field. So far these are the fields in the standard model of particle physics. Now, a problem of time 1 is also called background independence. No? So we know from classical mechanics, from Newton's absolute space and time, and also from the Minkowski space-time or special relativity, there's a fixed background. Fixed means non-dynamical. It's just a stage, and the fields are dynamical. They are the actors on that stage. Now, in general relativity, this is no longer the case. There is no fixed background anymore. I mean, the stage becomes part of the actors. And this is what is background independent. So if you then later try to quantize, you can no longer do what we do in standard particle physics, quantize on a background. And it was clear, I mean, from the first talk, what are the challenges in doing this, right? So Einstein once wrote, it is contrary to the scientific mode of understanding to postulate a thing that acts but which cannot be acted upon. So like the old absolute space-time, which is there, which cannot be acted upon, although it can act. So there are no absolute fields in general relativity. There's no background structure. Now, to see this more clearly and in more detail, I think it's most convenient to go to the canonical formalism of general relativity, to which I restrict myself here in this brief presentation in the metric formalism. And so we go from the Lagrangian to a Hamiltonian formalism, and this was already done very early. The earliest paper I know on this Hamiltonian is by Felix Klein in 1918, so relatively short after Einstein's pioneering paper. So to summarize, Einstein's equation can be written as a dynamical system, and it's a dynamical system for the 3 metric called HAB here, and its canonical momentum pi AB on a space-like hypersurface that I call sigma of evolution equations, which are not written down here. So the 10 Einstein field equations that you saw earlier are split into 6 evolution equations, and these are on display here, 4 constraints. With 4, I mean 4 local constraints, 4 times infinity cube, if you like, at each space point. And they are called the Hamiltonian and the Hamiltonian constraint and the 3 momentum constraints. Okay, so they have here this kinetic part and this potential part, and this is from the right-hand side of the Einstein equation from the T minus, the matter part. And so HAB is the 3-dimensional metric. H is its determinant. This is the 3-dimensional Ricci scalar, the energy density of matter, and here you have the canonical momentum attributed to the 3 metric, which is constructed out of the second fundamental form. That is classically how the 3 metric is embedded into the 4th dimension. GABC is the de Witt metric, which is written here, but which I don't go into details. It's a metric on the space of metrics, or the metric on configuration space. Kappa is 8 pi g over c to the 4. So these, in a sense, encode all the structure and all the dynamics of general relativity. And this is brought, I mean, to explicit light by understanding the connection between the constraints and evolution. Now, I've tried to summarize this on this transparency, giving the so-called interconnection theorems. Now, first is the constraints are preserved in time. And time means they are valid on each spatial hypersurface if and only if the energy momentum tense of matter has vanishing covariant divergence. So this gives you a direct interaction relation between, I mean, a very important relation for matter, this covariant conversation law, and gravity. So in electrodynamics, you have a similar theorem. The Gauss constraint, nabla E is 4 pi rho, is preserved in time if and only if there's charge conservation. Now the second theorem states that, okay, if you have these 3-dimensional hypersurfaces and if you demand the constraints to be valid there, then the connection between separate hypersurfaces has to be done by Einstein's evolution equations, by the remaining 6 equations. And so you don't have to postulate the extra 6 equations if you demand that the constraints be valid on each and every hypersurface. So Einstein equations are in fact a unique propagation law consistent with the constraints. Now in electrodynamics we have a similar statement that Maxwell's equations are the unique propagation law consistent with Gauss constraint nabla E is 4 pi rho. So this makes it also plausible why in the quantum theory, in principle, you only need a constraint and you don't have to deal with the evolution equation. If you restrict to compact 3 space, I don't talk about the boundary terms of asymptotic flat space-time here, then we can say that the total Hamiltonian is a combination of pure constraints, and all the evolution in this sense just said is be generated by the constraints. There's no external time parameter anymore because all there is space-time, and all physical time parameters are to be constructed from within the system that is as function of the canonical variables h, a, b, and p psi d. A priori, there's no preferred choice of such an intrinsic time parameter. Now, the absence of an extrinsic time and the non-preference of an intrinsic one is known as the classical version of the problem of time. But still, space-time exists. Now comes the quantization, and I restrict myself in this short time to the quantization of these canonical equations in metric variables. There's much to say, of course, about this in other approaches, such as loop or string theory. Now, John Wheeler and Bryce DeWitt in the 1960s, after, of course, earlier work by Dirac and the Bergman group and ADM, they presented and, of course, discussed the quantum version of the constraints. And as I emphasized, all there is in the constraints. And so we have this h psi equals 0 and h a psi equals 0. So that's the standard quantization. I can say much about this, but time does not permit. So you have here from the pi ABs, the second derivatives, that you have the DeWitt metric and the potential term. And this is called the Wheeler-DeWitt equation. And the quantization of the 3 other local constraints, this leads to the quantum diffeomorphism or momentum constraints, here, which look very simple, and this looks more complicated. I don't talk here about the issues of factor ordering and so on. Now, John Wheeler on the blackboard, and he was famous for his blackboard talks, that also I remember to have seen one live. What is the difference between the classical and the quantum in the particle case and in the gravity case? And this is summarized here in this table that perhaps you recognize from Misnoson and Wheeler, whose 50th anniversary we celebrated recently, but in a review with Patrick Peter from Paris, in a review on time, we modified this a bit according to our own taste. So here you see the underlying motion. Geometrodynamics, this is John Wheeler's word for Einstein's theory for general relativity, and particle dynamics. So particle corresponds to space, the events to 3 geometry. Now, what is a trajectory in mechanics becomes then a 4 geometry in gravity, HIT from T. Here space-time actually corresponds here to superspace, the space of all 3-dimensional geometries, which is actually the configuration space, and which is the space, of course, infinite dimensional space on which then the wave functional of quantum gravity lives. So there is no additional time. Now here you have an additional time because in classical mechanics you have this external time in addition to the trajectory, and then you quantize, the trajectory is gone, the wave function remains, but absolute time is of course still there. Whereas here there is no space-time and absolute time in addition. So if you quantize space-time, everything is in here in the 3 geometry. Now this leads to the problem of time 2, or the quantum version of the problem of time, that the space-time has vanished from the formalism in the same way as the trajectory of the electrons, say, and atoms have vanished in quantum mechanics, and only space remains. And this holds for loop, also for loop quantum gravity, and probably also for string theory, although on the latter a more subtle discussion is needed. And perhaps we will hear about that later this week. It's not special now or for quantum relativity. It holds for any theory that classically is reparameterization invariant. That is, for any theory that classically has no absolute time in addition to space-time. Now the Wheeler-DeWitt equation has the structure of a wave equation. So if you look more carefully into this object, it has one minus and a lot of pluses. So it looks like for an oscillating string, a wave equation. So you can define, just from the structure of the wave equation, out of the 3-metric, an intrinsic time. Now the Hilbert space structure in quantum mechanics is connected with the, as already Pauli has discussed, with the probability interpretation and especially with unitarity, so probability conservation in time. So of course the question is what happens with that, and in particular with the notion of unitarity in a timeless situation. Now, I fear, of course, that I run into a problem of seminar time, so I have not included here this kind of the relational observables, because there will also be talks about later. So, so sorry for that restriction in time. But I will mention that this is just a cartoon for the absence of time in quantum gravity. Now, the full Wheeler-DeWitt equation is, of course, complicated, but you can, and this is what is commonly used, discuss it without mathematical ambiguities for finite dimensional systems. And this is the realm of quantum cosmology. So if you consider here a closed Friedmann-Lemaitre universe with the scale factor A containing a homogeneous massive scalar field phi, which is a two-dimensional so-called mini-superspace that Charles Meissner coined in 1969. So with the classical line element here written down here, and the Wheeler-DeWitt equation in a convenient choice of units written down here. So you see the kinetic term, you see this hyperbolic indefinite structure. Here the derivatives with respect to the scale factor, the size of the universe A, the field, and the potential term. And out of the 3-metric and the matter fields, only 2 degrees of freedom remain, the scale factor A and the field phi, which is homogeneous. And this is certainly an equation that you can discuss consistently, either in some cases analytically or in most cases numerically. Now for the topic time, there is one important issue, which is I tried to illustrate here on that picture. Namely, there is a different concept of determinism in classical and quantum theory. Now, the classical configuration space is A phi, and if you have a recollapsing model of a universe, you can, for example, give here initial conditions, have a maximum and recollapse. Of course, you can also start here because you just have the trajectory, there's no direction. So in this sense, the recollapsing part is the deterministic success of the expanding part. But in the quantum version, the trajectory is gone. You have a hyperbolic equation, and for a hyperbolic equation, you give as initial conditions the psi at A, and also its derivative, A equals constant. That is, if you want to construct a wave packet here, following this, then you have to put the wave packet here and here, because A equals constant is the initial value region for the wave equation. Now you don't have the trajectory. And so, in a sense, the recollapsing wave packet must be present initially with respect to A. And if you do not do that, you get a very weird solution and certainly not wave packet. So in a sense, there's no intrinsic difference between Big Bang and Big Crunch in quantum gravity. Now, okay, some time ago, I discussed wave packets, and for example, for this equation, this is the indefinite oscillator. It comes from coupling a Friedmann universe with a conformally coupled field and rescaling. But the point is, it's the so-called indefinite oscillator, as simplest as you can have, like the harmonic oscillator in quantum mechanics. And then you really classically, you have Lissajous ellipses. And if you construct a wave packet, you see here a superposition of these Lissajous ellipses, but you have to really put here these 2 initial conditions here, the 2 wave packets, the one from, if you like, the Big Bang and the one from the Big Crunch. Otherwise, you get just a mess. Now, in 1919, I gave a talk actually in front of John Wheeler and Bryce DeWitt in Santa Fe, and Bryce DeWitt was very happy that I have here this boundary condition for the classically forbidden region, psi going to 0 as in quantum mechanics, because at that time, I mean, the no boundary proposal was very popular, but it gives solutions exponentially increasing into the classically forbidden region, which DeWitt was absolutely not amused by, to have this in contrary to quantum mechanics. So you can construct solutions that fulfill classically forbidden going down. So later, actually, in the year thereafter, I showed that in the no boundary proposal, actually these solutions cannot be found from the path integral by going through all types of contours, because the solutions either diverge at infinity or at the light cone in mini-superspace. Now, okay, Chairman has time under control, probably started a bit later, I think. So, of course, from this timeless situation, you should at least be able to recover semi-classical time, and I only have it here in text. No? So if you expand the Wheeler-DeWitt equation with respect to the Planck mass, you get a functional Schrödinger equation for the non-gravitational fields, and in a space-time that is a solution of Einstein equation. So you can recover, but in an approximation only, the time of classical Einstein theory, with all its covariance, of course. And this is also called WKB time, and the approximation scheme is a Born-Oppenheimer type of approximation, where you can then get the usual Hilbert space structure and its associated probability interpretation. And maybe the first paper doing it was Lapchinsky and Rubakov's paper in 1979, and also some other work in the 80s. Okay, then you get a pointer at least, but not yet a direction. Now, we thought about then going beyond that and having maybe quantum gravity corrections to this functional Schrödinger equation. And actually, the next order gives a functional Schrödinger equation with the WKB time, but with the matter Hamiltonian supplemented by 1 over Planck mass squared corrections that I did not write down. So with T.B. Singh from the Tata Institute, we did this, and later with Andrei Bawinsky from the Lebedev Institute, we translated these correction terms into covariant Feynman diagrammatic language. Now, of course, interesting is whether you can observe these things and arrive at a quantum gravity prediction and confirmation. For example, it contributes to the cosmic microwave background. So does the anisotropy spectrum of the cosmic microwave background radiation contain information about quantum gravity? And here again, I don't give you the details. Also, it's not directly related to the topic, but I refer to our recent review with Leonardo Chatenier and Paolo Muniz and all the references. And also Leonardo has a poster here. Also, I think there is about the relational observables, where you can also find this, and also the connection to observations. In a sense, one could also say that some quantum gravity effects have already been observed, because even without these corrections, what you usually do in this context and having an inflationary model is to use these Mukhanov-Sasaki variables, which include which then quantize these, and this includes already a quantization of the metric at a linear level. And then you get the power spectrum, which is proportional to Planck time times Hubble parameter squared, which you could say is a test of linearized quantum gravity. But here, would be beyond that. Now, the coherence, which was mentioned. What is the coherence? The coherence is the irreversible emergence of classical properties by interaction with environment, and is something that has been discussed long ago in quantum mechanics. And so I transfer this also to gravity. But okay, what is their system? What is their environment? And it was suggested that system, these are the global degrees of freedom, such as a scale factor, and the environment are small density fluctuations, such as tiny gravitational waves. Environment does not mean something outside the universe. Everything here happens in configuration space. So the configuration space of all variables is divided up into relevant and irrelevant part. And for example, one example that we discussed with Barwinski and Kamenschik was that we have this semi-classical de Sitter universe inflation, and that we have the coherence by the interaction with gravitons, with small unobservable gravitational waves, so that the local density matrix gets modified by having here this suppression of non-diagonal terms in this way, which means that the superpositions that you have here, of course, in quantum gravity, say with different scale factors, gets suppressed. So the universe also assumes classical properties at the beginning of inflation, and time, in a sense, can also be understood, or the emergence of classical time by this decoherence or by symmetry breaking, because to arrive at semi-classical WKB time, you have to have an e to the is state for the gravitational field. Now you could also add the e to the minus is to arrive at a 1 minute, okay? This is the real problem of time. And so in a sense, there's also this analogy with sugar molecules, where we have the parity invariant Schrödinger equation, but you have parity non-invariant states, such as chiral sugar states, and they become decohered through interaction with photons, no? Optical activity. And in here, of course, you have then e to the is and e to the minus is, and this decoherence between the two can be done, for example, with weak gravitational waves that has also calculated. Yeah, okay, then maybe I skip then the last part of the arrow of time, unless someone asked in the discussion session. It's only 2 slides, but I just mentioned this decoherence of the primordial fluctuations, because they are quantum fluctuations, as I emphasized, both the metric and the inflaton field. But this decoherence is also important, because to serve as classical seeds for structure formation, they need to be classical, and this is also done with Polarski and Starobinski we discussed some time ago. And yeah, okay, I skip the arrow of time and leave you with that picture. So these are the decohered quantum fluctuations of the early universe. So thank you very much.
So thank you a lot for this.
Yeah,
very
time
nice
runs too quickly, I must say.
Yeah, time is heavily running here in Nijmegen. Are there questions? Yes, please.
Klaus, thank you for a very nice talk. The work that you did with Paolo Moniz that you mentioned in passing, that you can actually see quantum features in the anisotropy of the background radiation. You mentioned that when you see stochastic behavior, it's a strong indication that it is quantum. I just want to comment, I don't know whether that's what you really meant, but there's a big gap between quantum and stochastic. And in fact, in the literature, people usually say we'll do quantum cosmology or quantum mechanics, but let's assume that it could be substituted by a stochastic classical source. And that's a big mistake usually. I'm not saying that you're doing that.
No,
I just want to clarify.
I fully agree with doing it. It's just not done that, because what we did, I mean, there's nothing to write here, but well, maybe otherwise I would start giving a lecture. But yeah, no, that's you have this Schrödinger, functional Schrödinger equation, which is a Schrödinger picture analog of quantum fields in curved space-time. This you recover as an approximation, and then to this wave function you get really quantum corrections 1 over mp squared, and this stochastic behavior here only comes then after you take into account the coherence, and so it's not put in at a fundamental level. So it's really, like for example, if you take the Dirac equation and you recover that in a 1 over c squared approximation, the Schrödinger equation and this Foldy-Wuthuysen transformation, and then you get 1 over c squared corrections to that. That's the analog to that. So really quantum and not stochastic.
The quantum features, yeah.
Yes, can you say something about the older definition of the problem of time variable in canonical quantum gravity, where it was defined as finding a canonical transformation such that your Euler-de Witt equation is transformed into Schrödinger equation, effectively?
I could also say that. You mean the reduced approach, right?
Yes,
yes,
if you fix the time in the end.
I of course had to exclude all of this here in this very short time. This is what, there's just nothing to write. So, I mean, you can, just what you have this classical h equal to 0, then this would mean to classically reformulate to identify a time, because you have this ambivalence of choosing many, and write it in the form pt plus h reduced equals 0. Yeah? And if you have this pt plus h reduced equals 0, you can then write the pi t transformed to h power over I t over dt, and the h reduced to h operator reduced. And then you have a Schrödinger equation. And that's the reduced approach that has been followed from the very beginning. In particular, Karel Kuchasz has done a lot of important work on it. The point is, I mean, he also proved various theorems, various no-go theorems, that you cannot globally do that. Yeah, so it prevents, I think, also by Torre. Charles Torre has theorems of 93. And even for those cases where you can, it's very hard to do explicitly, because typically you get this h reduced as some square root terms, say square root of momentum squared plus a complicated functional of q. And so you have to quantize this square root. And it does not take very long, then you are stuck with that. So this is maybe a short answer to that. But in principle, of course, that's a valid alternative to think about.
Yeah, one brief question by Sumati, and I think then we have to break for coffee.
This is a general question, but about these. Here you talk about gravitons helping decohere. Of course, the whole system, I mean, it's a single system, it's a closed system, but you're choosing to divide into things that, you know, in something like Born-Oppenheimer you might want to do. So are there scales involved in here when you do such a decoherence, which allow you to treat one part of it as system and one part of it? So in other words, what uniquely determines that division? This is sort of...
Yeah, good question. This is, of course, at the center of this decoherence approach, and there is no God-given unique division, because you divide up into relevant and irrelevant degrees of freedom. And if you think about quantum mechanical examples, then what is relevant and what is irrelevant can differ from one case to each other, right? If I want to have, say, if I have an interference term, an interference experiment, for example, the ones that have been done in Vienna with Buckminster fullerenes going through interferometers and producing interference patterns, they discuss decoherence in two ways. First, they have a vacuum, but they introduced a gas into that. And then the gas was the environment that decohered the interference of the Buckminster fullerenes. But in other experiments, they just heated up the fullerenes, and this led to emission of photons. So in that case, actually, this environment came from the system itself, in a sense. Yeah? But the point was it emitted photons that were no longer under scrutiny, that you could not observe. No? So in a sense, in quantum mechanics, it's up to the genuity of the experimenter to really know what is relevant, irrelevant. So you already